This video is an additional supplement to your class notes from today on graphing rational expressions. The first thing that I do when I get a rational expression, such as number 3, is I factor the top and the bottom. And the reason for doing this is to see if this fraction can be reduced. So I would reduce this fraction by factoring a -4 out of the bottom and then you can see that nothing can cancel out on the top or the bottom because there are no groups that are exactly the same. In order to find an X-intercept, I would always make y equals 0. But in this case, when I make y equals 0, all I really need to worry about is where the numerator of the fraction equals 0. So I would go ahead and set the numerator equal to 0 and solve for x. That gives me the X-intercept. That means on my graph, I'm able to graph a dot on x's 4. The Y-intercept. In order to find a Y-intercept, you would make x equals 0. So in my equation, I would have y equals 0 minus 4 over -4 times 0 plus 4. Or you could put x is 0 back in the original equation. If I put it in the original equation, I can see I'd have -4 times 0 minus 16. In either case, you get -4 on the top, and you get a -16 on the bottom, and that can be reduced to 1/4. That tells me that this graph is going to cross the y-axis at 1/4. So I'm going to go ahead and make a dot approximately where 1/4 is. A hole in the graph occurs when you can cancel something in the numerator and the denominator. But in this particular case, the x minus 4 and the x plus 4 are not exactly the same. So they cannot be canceled, so there are no holes in the graph. The vertical asymptote would be where the denominator equals 0 and you would find that after canceling and looking for holes. So the only place where the denominator equals 0 is where x plus 4 equals 0, or where x is equal to -4. That tells you there's a vertical line at x is -4. So you can go ahead and go over to the graph and go to where x is -4 and draw a vertical guideline, keeping in mind that the graph cannot cross that x is -4 value. Horizontal asymptote. In this particular case, we're always comparing exponents to find the horizontal asymptote, and we discussed how there's 3 cases. There's the case where the top equals the bottom, when the 2 exponents are equal. Remember, we divide the leading coefficients. If the top exponent were smaller than the bottom, it would follow the line y equals 0. And if the top exponent is greater than the bottom, then there is no horizontal asymptote. So in this case, I can see my top exponent is a 1, my bottom exponent is a 1, so I'm going to go ahead and divide these leading coefficients. The leading coefficient on top is 1, the leading coefficient on the bottom is -4. That means there's a horizontal line at y equals -1/4, and I would go ahead and draw approximately where that line is. I can now start drawing my lions that are pacing back and forth in the cage. So I can see that the lion would be pacing this way, going through those 2 points, and then he would also be coming up this way and staying in the cage on that side. I know that there must be a lion on the other side of that cage as well. There's always 2 lions, it seems to be, in these pictures. So I'm going to go ahead and I'm going to take x is equal to -5, which is over here. And I'm going to go ahead and substitute -5 into the original equation. So that would make -5 minus 4 over -4 times -5 minus 16. That would give me -9 over 20 minus 16, which is 4. That's -2 1/4. So when x is -5, y would be -2 1/4. That tells me that's where my lion is located, and he would be following the cage down here. The domain for this problem, x can be anything except for the vertical asymptote. X cannot be -4. And the range, y can be anything except for the horizontal asymptote in this case, except and the horizontal asymptote is -1/4. So y can't be -1/4. Example 4. Again, before I attack the problem, I see if the top and the bottom can be factored. And I can see that the top can be factored into x plus 3 times x minus 3. And the bottom can be factored into x minus 3 times x minus 3. That tells me that the x minus 3's can cancel, and it would leave me with x plus 3 over x minus 3. So what do I do with that? Well, let's go through things one by one. So for X-Intercept, you look at this reduced equation to find this. This is the easiest way to go. This is the equation y equals x plus 3 over x minus 3. An X-intercept would happen when y equals 0. And if I set a fraction equals 0, the only thing I worry about is where does the top equal 0? Because I know the bottom can never equal 0. That means the X-intercept occurs at -3. I can go ahead and make a dot at -3, 0. The Y-intercept occurs where x is 0. Again, you can put x is 0 in either the original equation, or you could put it into your reduced equation. Either way, you will get the same answer. To find y-intercept, you make x equals 0. So I'm going to go ahead and make x equals 0. I'll use the reduced form. So I went ahead and put 0 into the reduced form. When I reduce, I have 3 over negative 3, which is negative 1. That tells me the y-intercept is 0, negative 1. The hole in the graph. The hole in the graph comes from things that can be canceled. So I can see that I had an x minus 3 over x minus 3. If I set that equals 0, I find out that x can't be 3. Because if x were 3, it would make 0 in the original denominator. And I can never divide by 0. So again, to find the hole in the graph, you look at the factor that you canceled. You set that factor equals 0. And that gives you where the hole in the graph is located. But the hole needs to be a point. So I'm going to go ahead and I'm going to plug in x is 3 into the new equation to find out what y is. And I put it into the new equation after canceling. And I find out, oh, wait, that's undefined. It's undefined there. So it looked as though that would be the x-intercept. Actually, it's not the x-intercept. The x-intercept was negative 3. The hole would be normally at 3, but because we're getting undefined here, and we're not getting a y value, what that means is it is the vertical asymptote. And you can see from what's left over. Let me highlight what's left over here. What's left over here? The bottom can't be 0. So that means that x still can't be 3. So this is kind of a weird case. Your vertical asymptote would be where x is 3. That means that I have a guided line right here, vertically. So it's not a hole at all. It's actually a vertical asymptote. Again, I found out it's not a hole because when I plugged 3 back into the equation, the new equation, after canceling, it still comes out to be undefined. So it's a vertical asymptote, not a hole. All right, horizontal asymptote. So now that's where I compare my leading coefficients, and I can see that they are, the exponents are the same on the top and the bottom. So that means that I can go ahead and divide the leading coefficient on top by the leading coefficient on the bottom. And that gives me the equation y is equal to 1. I can go ahead and draw a horizontal line at y equals 1. So now you can see you've got these cages going on here. This is a wall of a cage, and this is a wall of a cage. Now we're going to draw our lions. So first of all, I've got 2 lions, or 1 lion that's here, and I can see he has to go through this other point. So it's going to end up looking like this. And he's going to stay in the cage. And again, I know that there's another lion on the other side of the cage wall. So let's try x is 4. When you go ahead and you substitute in x is 4, you can put it in the original or even in the reduced version. I end up with y is 7. So when x is 4, y is 7, which is up here. That tells me this lion needs to scoot along this cage, and he's going to come down like this, and he's going to scoot along that cage. The domain is everywhere except where the vertical asymptote is. So all real numbers except x can't be 3, because remember, domain is all the possible x values. And the vertical asymptote tells you it can't be 3. The range is all real numbers again, except x isn't where the horizontal asymptote is in this particular case. So, except where y, because we're talking about y's now, except where y cannot equal 1, because that's where my horizontal asymptote is. Okay, so hopefully that gives you a couple other examples that you can reference. Again, keep in mind, when you're looking for X-intercept, you're making y equals 0. Essentially, you're setting the numerator equals 0 and solving. The Y-intercept, you're making x equals 0 and you're solving for y. Hole in the graph happens when you can cancel the top factor and the bottom factor. Vertical asymptote, any factors left on the bottom. Any factors left on the bottom would be set equal to 0 and solve, and that gives you your vertical asymptotes. Horizontal asymptotes are your 3 rules for exponents. If the top equals the bottom, you divide the leading coefficients. If the top is smaller than the bottom exponent, then it's y equals 0. And if the top is greater than the bottom exponent, then there's none. The domain always ends up being all real numbers except for the vertical asymptote. And the range ends up being all real numbers except for the horizontal asymptote in the cases of rational expressions.